Hello everyone, let's solve some Leetcode today. So today we have Leetcode 111, that is minimum depth of a binary tree. In this problem we will be given a binary tree root and we have to find its minimum depth. The minimum depth is basically the number of nodes along the shortest path from root node down to the nearest leaf node. So basically we have to find the nearest leaf node, and the leaf node is simply a node that have no children. So in the example here we can see that we have 3 here, and then the nearest leaf node is this one, 9, because 9 does not have any children. If you look at 20, the children are here, and the 15 and 7 are leaf nodes, but they are further from the 9. So 9 is the nearest leaf node for 3. So what will be the minimum depth of this tree? Well, it is going to be simple 2. Why? Because the minimum depth is the number of nodes along the shortest path from root node to leaf node. So there are 2 nodes on the shortest path in this tree, including the root node and the leaf node. That's why we are saying the answer will be 2 for this tree. Now in my understanding, there are 2 ways to solve this particular problem. We have DFS and then we have BFS. So DFS is the common way to solve this. You will find a lot of videos online for DFS solution. But BFS is something that I find more intuitive because it will tell me on which level we find the first leaf node. So if we look at the given example here, we see that we have levels. Level 1, then we have level 2, then we have level 3. And this level represents the number of nodes from root to this particular level on a single path. For example, here we have 2. And what this represents is that if you start from the root node and you go in any path, then till here, you will have 2 nodes on that path. As you can see that we have 1 node here and then 1 node here. On this path also we have 1 node here and then 1 node here. So this simply represents the number of nodes from the root node on a single path to this level. Now since we are going to use BFS for the solution, let us understand how it works. So now let us understand how we can use BFS to solve the particular question. So in the BFS, we usually have a queue that will keep track of the elements or the nodes that we are going to traverse in the current level. So for example, we are going to traverse the level 1 in the starting. So we are going to have 3 in the queue. So 3 is here in the queue. And now what we will do is we will pop this 3. So the 3 will be popped, and then we will have a condition. If this particular element is a leaf, we simply return the level. We are going to return the level we are traversing as soon as we find a leaf node. So we will be having a level variable that will store the current level we are traversing in the BFS. So we will start with the 0, and before popping the elements, we will set the level to +1. So level is equals to level +1. We will increase the level because we are now starting to pop the elements. But in our case, the 3 is not a leaf node, so we will continue and add left node and the right node of 3 into the queue. So we will be adding 9 and 20. So let's add a 9 and then add 20. And now since 3 has been popped out, so we can simply mark it done. 3 will not be in the queue anymore. We will have 9 and 20. And now we will take the 9. So element will become 9 here. And now we will check, is element is leaf? Yes, element is leaf because it does not have any left or right children. So now we will simply return the level. And remember that before we popped out, we actually changed the level to +1. So we started with the level 0, then we went to the 3. So the level actually became 1 at that time. And now we are actually at 9. So the level will +1 and it will be 2. And so we will simply return the level, and that will be the answer. So what we are doing is we are traversing the graph from root node. So we will have level 1, then we will have level 2, and we return the level as soon as we find a leaf node. Because this is going to be the first leaf node that we encounter after starting the BFS, and it means that any other leaf node after that is simply going to give a greater depth. So we need the minimum depth. So we simply return the level as soon as we find a leaf node. Now one thing I want to point out is the number of nodes in the current level. Suppose we are at the level 2. So how will we know that out of the elements present in the queue, how many elements actually belong to level 2? Because as we are traversing the levels, we are also adding their children into the queue. So the queue size will keep on increasing, but we need to know which node belongs to which level, right? So we will be doing with the help of this particular line. So when we will start the while loop in our DFS, first and foremost thing we will check is the number of nodes on the current level. And the number of nodes on the current level will be equal to the length of the queue at that instance. So for example, I start with the 3. The first thing in the queue will be 3. So I'm starting with the 3 node or the root node. So here on this line, I will get the current level as 1, correct? Because the length of the queue is 1. And then based on this number, I will run a for loop. So for I in range current nodes or the current number of nodes, I will run the for loop. And then we can pop the element. And note that before starting the for loop, we will simply update the level to level +1. So level will be starting with the 0. And in case of 3, here we are updating it to 1. The level will be now 0 + 1 = 1. And now we can start popping. So we can pop the element 3, and then we will will check if it is a leaf node. It is not a leaf node, right? Then we will go down and we will add the children, that is 9 and 20, into the queue. And as you can see here, that this for loop will only run for this particular variable, for this particular range, the number of the current nodes on the current level that we already calculated. So as we popped the element 3, the for loop will run, and then in the next iteration the for loop will end because we have exhausted the node. And then we will go back to the while loop. We will check if queue is not empty. Yes, currently it is not empty. So we will again check the number of nodes in the queue, and this time the number of nodes are 2. So this will be 2. And now we are again updating the level to level +1. So 1 plus 1 now will be is equals to 2, right? So level will be 2. And based on this variable, this for loop will now run for 2 times. So in the first iteration, we will pop the 9 and we will check if it is leaf. Since it is leaf, we will simply return here the level, and level currently it is 2. So our answer will be returned and the 9 will be popped out, of course, and our BFS will simply end. Now there is one more edge case that we need to look out for, but we will see it in the code itself. So now let us go through the code. First of all, we have the level equal to 0. Then we have the queue in which we will track the number of elements we have to deal with in the current level. Then here we are appending the root in the queue because we need to start from somewhere. So earlier the queue was empty. Now we are appending the root. So we will start from the root. And now we are starting our BFS solution. So we are checking if the queue is empty or not. If queue is not empty, we will start the BFS, and then we will take the number of nodes on the current level. And here I am increasing the level by 1. So the level at this point is 1 for 3, and here I'm starting the for loop for the number of nodes in the current level. Now the first thing we do is pop the element from the queue and we check if the element is none. This is the edge case that I'm talking about. So there can be a test case where you will not get the root node. So what will you do in that case? Well, nothing. You will simply let it continue. That will end the for loop, and the while loop will also end because there will be nothing more in the queue. So earlier when we were adding the root in the queue, we actually ended up appending or adding the none in the queue, and to handle that we have this condition. And since we are doing nothing, the entire while loop will end, and at the end here you can see that we are returning 0 directly. So it will handle the case where we have no nodes in the tree. So that will simply return 0. Now here we are checking whether the popped element is actually a leaf node or not. So if it does not have a right node and it does not have a left node, we will simply say it is a leaf node and we will return the level, effectively ending our BFS and sending out the answer. But if it is not the leaf node, we will simply append the left and the right node of the element into the queue. But if it is not the leaf node, now we are going to add the children. So if the left node of this particular element is existing, it is not none, we will append it into the queue. If the right node of this particular element exists, we will append that into the queue. And then the BFS will keep on running until we find the first leaf node. And as soon as we find the first leaf node, we will simply return the level. So now let us run it and see what happens. So yeah, it runs in 0 milliseconds and beats 100% solutions on Leetcode. Well, this particular number is not really trustworthy. Nothing can run in 0 milliseconds, of course, but it's a pretty efficient solution because we are using BFS, and BFS is an iterative solution. Yes, we do have a queue to track the elements, but the size of the queue will be less than the size of the recursive call stack of DFS. The space complexity will be the same, but if you look at the real amount of data that we are going to store in the queue versus in the stack, that will be different because stack will be storing a lot of other data that we don't have to deal with. So now let us look at the time and space complexity for this particular solution. So the time complexity for this solution is order of n, because we can have a tree which actually have all the nodes or all the levels completely filled. So we will end up going through all the nodes in all the levels just to find the first leaf node. And so we will almost end up traversing the n nodes, and that's why we are saying time complexity is order of n. And the space complexity is also order of n. But you will say that why, Satyam? We are also dequeuing the elements, right? We do have an element in the queue like 3, but then we dequeue it, we remove it, right? So why does this become order of n? Well, let us take the same example here. Okay, so we have number of elements as 1, 2, 3, 4, 5, 6, 7. So we have 7 elements. N is equals to 7. Now you will say that, okay, Satyam, when we are going through these levels, we are also just dequeuing this element, right? This element will be gone, this element will be gone, this element will be gone. And at the end, we will only have this last element or this last entire set of nodes into the queue, which is correct. So how many nodes are there in the queue? We have 1, 2, 3 and 4. Queue size is equals to 4. Now if you really look at it, 4 is simply n plus 1 divided by 2, which is 7 plus 1 divided by 2. So you can say in the worst case scenario, the size of queue will be n plus 1 divided by 2, which will be equal to n by 2 plus 1 by 2. So in the worst case scenario, this is the space that we will be taking up, which means the space complexity should be order of n divided by 2 plus 1 divided by 2. Now here's the thing, this is the big O notation, and in the big O notation we remove the constants. we don't need the constants. So it will actually become order of n by 2. But it is still not complete because we still have a constant here. We have n multiplied by 1 by 2. So we will end up removing this 1 by 2 also in the big O notation. Then it will become order of n. So that's why we are saying that the space complexity is order of n. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, then just let me know in the comments. Now we will meet in the next video. Till then, bye.